Okay, this is the continuation for the lecture video for section 4.3 in MAC 1105, where we are studying the remainder and factor theorems. We had done examples 1 through 6. This was the last example that I finished up with in the last video. And we are moving on to example 7. Now this one says that they would like the solutions for the equation given that this is one of the zeros. Remember, zero is just another name for solution. When you're looking at a graph, these solutions are the x-intercepts. In other words, where the graph hits the x-axis. So you can also call them x-intercepts. So zeros, solutions, answers, that is what you're being asked to find. This time they're telling you that this is a zero. That means when you synthetically divide this exact number, notice that it's not attached to an x as this one was. This was example 6. So they start off the directions slightly different, but you're really going through the same moves with maybe a couple of tweaks here and there. Like for instance, the difference between this problem and this problem is that they were saying use synthetic division. Well, we're going to use synthetic division as well. We have a polynomial that we were going to synthetically divide by a certain value, but here it was given as part of an expression. And when it's given as part of an expression, you must switch the sign before delivering that number to the synthetic division box. You know that you're going to be using it to find all the zeros, so the number that they're going to be giving you is going to zero out. That number itself is going to be a zero. It's going to cause this polynomial to zero out. Therefore, this is called a zero or a solution. Finding a zero, in other words, synthetically dividing a certain number into a polynomial such that the remainder is zero, also helps you bring down the degree of the polynomial. So whereas you might start with a third degree polynomial, you're now down to a second degree polynomial by the time you make that first pass, synthetic pass through the polynomial and get this remainder of zero. This was a second degree polynomial that I just went on to factor further and then found the second and the third answer. Please remember that the number of solutions will match the degree. So if you start off with a third degree polynomial, you can expect to have 3 solutions. And we had 3 solutions here. Sometimes you'll have a couple of matching solutions, but you will have 3 solutions. Okay, the only difference between example 6 and example 7 is the way that they are coming at you with the instructions. Now they're just saying solve the equation, but you're doing it through synthetic division. They're already telling you that this is actually one of the answers, and there's a total of 3. So being that this value is not combined, it is not part of an expression containing x, you will not be switching the sign as you deliver it to the synthetic division box. So once again, when the number that you're going to put in this synthetic division box is part of an expression containing x, as you break these two apart and break their bond, you will switch the sign of the number. When the number is given without being part of an expression containing x, then you will not switch the sign. And instead, you will deliver that value with the sign as is right to the synthetic division box. Okay, the rest of it is going to be the same. We're going to take these coefficients, make sure that none of the degrees are missing. We have third degree, second degree, first degree, constant. And take those coefficients and arrange them horizontally. Okay, so we have 16 for our third degree coefficient, 16 for our second degree coefficient, -1 for our first degree coefficient, and -1 for our constant. Put a line underneath here and drop the first value. You're multiplying any value that's below this bar by the number in the synthetic division box. So we're multiplying here. Now, if you can't do that in your head, which it's likely that maybe you won't be able to, then come over here. You need a little concentration on multiplying 1/4 times 16, negative 1/4. So it looks like this when you put it on paper, and that just means 16, negative 16 on the top, because it's negative 1 times 16 divided by 4. Negative 16 divided by 4. You can put that in your calculator if you'd like. So this times this is negative 4, and we always carry our answer right above that line. And then we combine. 16 minus 4 is 12. Now you're going negative 1/4 times 12. So negative 1/4 times 12, which is negative 12 divided by 4. And that's negative 3. And we carry that answer right up here. Combine these and you get negative 4. So now we're doing 1/4 times negative 4. So negative 1/4 times negative 4. And that is negative 1 times negative 4 is 4. 4 divided by 4, positive 1. And we carry that answer from the product right above the line. Combining any two numbers that are stacked upon each other, getting 0. Now, we already knew that this number right here, negative 1/4, was a 0 because they flat out told you that in the directions. So we have one of our 3 answers, and we are about to get the other 2, just like we did in this problem. We now had a second-degree polynomial. Well, you now have a second-degree polynomial suggested by these coefficients. It will be 16x squared plus 12x minus 4, and you would like to know what are the zeros of this polynomial. So what you're going to do is just continue factoring. I mean, you can write it like this. You can write that this polynomial, if you'd like, if you want to make it look just like the previous problem, not that it's necessary, is that this was one of the zeros. So if you wanted to write it in factored form, if this is a 0, then it looks like this when it's part of a factor. And what you had left over after you synthetically divided this value, which corresponds to x plus 1/4, what you had left is 16x squared plus 12x minus 4. And all you're going to do is, just like we did here, continue to factor. In other words, wanting to know what would make this second degree trinomial equal to 0. Well, anytime you're finding the zeros, you're bringing the polynomial all the way down to first degree factors, which can then simply be observed, and you can see what the values are that make it 0, thus finding the remaining 2 solutions. So what I think I would do here is I think that I would try to minimize the size of these coefficients. I see that 4 goes into each one of these, and I could make the numbers smaller and more manageable by dividing 4 into every single term here. So 4 goes into this 4 times, leaving you with 4x squared. 12x divided by 4 is 3x, and then negative 4 divided by 4 is negative 1. So at least you have smaller numbers to work with. Now, when you go to factor this, you can either use guess and check, where you just think about splitting up the front term as well as the back term in order to fill out the front positions and the back positions. When you're filling in the front positions, it's a question of what are the ways that I could break this down. You can either break this down into 2x times 2x so that you have first degree x terms, or you can break it down as 4x times x. Since I'm going for a 3x, I think I'm going to try 4x times x, and then when you fill in the back position of each one, you're thinking of, how can I break this down? Well, thank God this is a 1, because there's not a lot of ways that you can break that down, so thank goodness that that's a 1. All right, so let's see. The only way you can break that down is 1 times 1. But now thinking about the sign, I need to get a negative one. So one of these needs to be negative. If I allow this one to be positive and this one to be negative, I believe that will work out. And you need to be able to FOIL to check that all these terms are right and that you have the proper signs on this. You have to make sure that if you FOILed this out, you would indeed get this right back again. So let me check it real quick. 4x times x, 4x squared. That's right. This middle term comes from 2 of the products when you're FOILing. This is part of it. 4x times 1, 4x. That's part of it right there. Then this is the other part of it, and that would give you the 3x that you do have right there in the middle, so that works out. And then multiplying this times this gives you that last term. So that is factored properly. I wanted to know what are the zeros for these remaining 2 factors that came from this, which is just what you had left over here, but reduced form. Okay, so this one's really easy to look at. What would make this expression equal to 0 if you plugged in x equal to -1? Move that over just a bit. Okay, so we have some solutions. One that was given, the -1/4, one that I just observed, and this one, I don't know if you can do this one in your head or not. What makes this 0? If you can't think of, hey, what's the number that I could plug in there such that when I multiply by 4 and subtract 1, I get a 0, then you can just do a little side work. You could come over here and say, what makes 4x minus 1 equal to 0? And solve it like a little equation, which would mean you would bring the 1 over here. That would leave you with 4x equal to 1. Divide by 4, divide by 4. And you get x is equal to 1/4. And that is what would make this expression equal to 0, and therefore it's called a 0. Okay, so our third and final answer is positive 1/4. And these are the 3 solutions for example number 7. Okay, pretty much just like the problem right above it, only they start the directions off in a slightly different way. Okay, and yet here is another way to start off a problem where they give you a graph, and the graph suggests one of the solutions. Here they flat out told you verbally that this is one of the solutions, because that's what a 0 is. It's a solution of the equation. But here they're giving you a graph. And as I said, the solutions are also called x-intercepts. In other words, where the graph hits the x-axis, this is your x-axis, that is a solution, or what we call a 0. So you now know that x equal to 2 is a x-intercept, also known as a 0. Okay, which solution of the equation can be determined from the graph? X equal to 2. Because anything that's an x-intercept is also a solution of the equation, also known as a 0. Okay, what are the other solutions of the equation? Well, use the procedure that was used in both examples 6 and 7. We took something that we knew was a 0 and synthetically divided it into the polynomial to bring that polynomial down to second degree, and that's exactly what we're going to be doing here. We're just starting the problem in a different way each time. But all of the procedures and steps, once we know that we have one of the 3 solutions, is to take that, put it right here in this synthetic division box, copy the coefficients of the polynomial. So for my third degree term, coefficient is a 1. For my second degree term, coefficient is an 8. For my first degree term, coefficient is a -4. And for my constant, it's -32. Put a line under those values and begin the synthetic division process. Dropping down that first number and using the number in the synthetic division box as a multiplier. 2 times 1 is 2, Add these values. 2 times 10, 20. Add these values. 2 times 16, 32. Add these values, and you see that this number indeed is called a 0. And that's because it causes the polynomial to zero out in its remainder column. So we have already started our solution set. We knew from the graph alone that 2 would be a solution, and we just double verified that. You can see it on the graph, and you can prove it right here in the synthetic process. We did go ahead with the synthetic process because the synthetic process, you're not only proving that a certain number is a solution, you're also bringing that polynomial down from 3rd degree to 2nd degree. That's where we're at right now. So this 2nd degree remaining polynomial is 1x squared plus 10x plus 16, and we want to know what are the zeros of this remaining polynomial that is now in 2nd degree form. And we can factor this. Okay, so in this problem, let's see, if we were going to try and factor this, we could try and use 8 times 2 to get that 16, and 8 plus 2 also adds to 10. Remember, when you're factoring a trinomial, if you're using, especially when the first term is 1, you're just solving this little two-step process. You're looking for two numbers that multiply to give you the C value, but when added, these two values right here should also add up to give you the B value. And that would be 8 and 2, so pretty easy to factor. Okay, so breaking up the x squared, that's what fills in the front position of each of these factors, and then these numbers that we came up with fill in the back position of each factor. So we now have gone from a 2nd degree polynomial into 2 1st degree factors. And once you break it all the way down to 1st degree, you can tell what the solutions are. Okay, so what would make this factor right here equal to 0? -8. That is the 0 for this factor. What would make this factor equal to 0 if you plugged in a -2? And you are looking for the zeros, the things that create zeros, the values that create zeros in these factors are the solutions. So we already knew 2 was a solution from the graph. We proved it. We confirmed it by using synthetic. That confirmation also brought us down to 2nd degree. We then had a 2nd degree equation, which we factored down to 1st degree factors, and then we found the solutions, or what we call the zeros of each of those factors, which turned out to be -2 and -8. And those are the 3 solutions for a 3rd degree equation. Okay, let's see, what example are we on? So 7, this was actually the 8th example. And we are on to the 9th example. This one says use a graphing utility to graph the polynomial function defined by the left side of the equation. So we're going to put all of that in and get a graph for it in the y is equal to window. We'll type this right in, y is equal to window, but just this part, not the equal sign, not the 0. Making sure to use end behavior to make sure you have a complete graph. Okay, well, your graph is only as good as the person who controls it. So you need to know how to manipulate the calculator to give you what you want. When it says that you should be able to use end behavior, that is from the section right before this, section 4.2, where you should know what the ends behave like so that you know whether you're seeing the entire graph or not. Because how can you know whether all the solutions are being shown if you're not seeing the entire graph? So hopefully that makes sense. And in that section, let's review what we learned about end behavior. Okay, notice that the highest degree term in this polynomial is third degree. Therefore, this polynomial is third degree, which means it is an odd degreed function, a polynomial of odd degree. Anytime you are of odd degree, the ends will move in opposite direction. Okay, so one end goes up while the other one goes down. So that can mean two different things. It can go up on the right and down on the left, or vice versa, up on the left and down on the right. And that's why the degree, whether it can either be an odd degree or an even degree, the highest degree in the polynomial. This one happens to be odd degree. You then also look at the leading coefficient. The leading coefficient in this particular problem is just the coefficient that's in front of the variable with the highest degree. This is the highest degree. There is its leading coefficient. It's equal to -2. And anytime you have a leading coefficient that is negative and you're of odd degree, that means that the left goes up and the right goes down. So you want to make sure that when you do put this thing in the graphing calculator that you're seeing a left side that goes up and a right end that goes down. Make sure you're seeing the whole thing and not just part of it. Okay, so here we go. We're going to go to y is equal to whenever you want to graph, and you're going to put in the terms that you see right here. Not the equal sign or the 0. Just right up to the -10x. So it's -2x raised up to a power of 3 plus 12x. Put a square on it. You can just press the x with the little square on it, or you can put raised to a power of 2, either one. And then it's -10x. Now one window, don't forget to press enter so that the calculator absorbs every single term, including the last one, the -10x, for that polynomial. A good window to just like start with, and then you can see whether certain portions of your graph are chopped off. That's why you have to have a sense of, hey, what do the ends look like? Because if you don't know that, then you don't know if you're seeing the whole graph or just part of the graph. So a nice window to start with might be Zoom, where all the pre-made windows are, and choose a standard window. That's -10 to 10 on your x-axis and -10 to +10 on your y-axis. Let's see what it looks like at that point. All right, here we go. But one thing is that we are trying to very clearly see the solutions, and when there are too many numbers on your x-axis or your y-axis for that matter, but specifically we're interested with the x-axis because that's where the x-intercepts are, and those are the solutions. So when there's a bunch of numbers on there that aren't needed with respect to the graph, I'm seeing most of the whole graph. Maybe I'm not seeing the top, but I don't need to see the top because I want to know where it hits the x-axis. For purposes of this question, I would like to clearly see what's going on here. I don't need all this. This is all space that is not doing us any good. This is space that's not doing us any good. So if you have less numbers on your x-axis, you will have a clearer representation of where it's hitting the x-axis. Looks like this hits at 1, 2, 3, 4, 5, 6. Why don't we go out to 6 at least? And as far as how far we're going to go this way, we don't need to go to -10. Why don't we just go to -1? So now we are going to manually manipulate this graph. We're going to go to Window. See here there was a pre-made window. When we chose Zoom Standard, that automatically set this window from -10 to 10 and from +10 to -10. We don't need that. So let's go here and let's do less on the x-axis, which will stretch out the graph and give us a clearer view of the x-intercepts. Let's just go to -1 on the negative side, not -10, because there was nothing going on over there. And let's go as far as +6 on the x-axis. Press enter after you've changed those two values, x-min and x-max, and graph it again. Now we have a much nicer view of the x-axis. Again, you can't see the top, but that's not where you get the solutions from. If you were being asked a question like, hey, what is the max? Then you'd need to see the top of it. So then you would manually adjust how high your graph goes on the positive y-axis, but we don't need that here. It appears that this graph has an x-intercept at 0, an x-intercept at 1, and an x-intercept at 2, 3, 4, at 5. If those truly are answers, 0, 1, and 5, if they truly are answers, then they will have y partners of 0. Anything that is truly an x-intercept and therefore classifies as a solution, or what we call zeros. And here's the reason why they're called zeros, because their y partners will be 0. So what you want to do is you want to check the y partner for each of these on the calculator using second table. Okay, so I'll just write it here. Check the y value for each of these potential solutions. Or let's use the name that we're being really prompted into using quite a bit in this section, for each of these potential zeros. Okay, the y value for each should be a 0 itself. If the graph is really hitting, and I tell you to check them only because sometimes when you're looking at a graph, it looks like it goes through, let's say 1, and it's really 1.1 or 1.2. Just such a slight difference that it's really not visible to the eye. So the way you can check it is by going to second table. Okay, so we're going to make sure and go to second table to check things out at the x values 0, 1, and 5. So second table is just a graph key. Okay, so I think that at the x value 0, let's see what's going on there. Notice that it has a y partner of 0, and therefore this is a solution. Okay, then I want to check out the x value called 1 and see whether or not that's a solution. So mosey on down to the x value 1. Notice that again the y partner is 0, and therefore 1 is also a solution. If it has a y partner of 0, then the actual value you see here is the solution. Okay, then I'm going to go down to 5. Notice that it also has a y partner of 0. And so this is also a solution. So our final solutions are 0, 1, and 5. Okay, that is the final set of solutions. Okay, so that time we started with a graph. We used the solution on the graph to synthetically divide into this polynomial x cubed plus 8x squared minus 4x minus 32. We brought that polynomial, third degree, down to second degree, factored our way to two other solutions in this problem. And then when we got to this problem, we had an example where we used our own graphing utility. Here they provided the graph for us, and then we went a little further in this particular example, creating the graph ourselves. Remember that we went to y is equal to and fed it in. We started off with a standard window, and where we found a standard window was just zoom standard. Then we saw that there was just way too many numbers on the x-axis, so we touched the window key and decided to make our x-axis like this. We went from -1 to 6 with an x scale of 1. So in other words, this is the was the x min. I fed in that value. I changed it from -10 to -1. I fed in this value for x max. I changed it from a 10 to a 6. And then the x scale was already there. This is what we call x scale. You might as well be reminded. This was from the very first chapter that we did in this course, where one of the sections was about manipulating your calculator to get a proper graph. Okay, so now we're using it to solve equations, using the graph to get us started. Okay, moving on to example number 10. Okay, so this is the 10th example that I'm giving regarding these concepts that revolve around synthetic division. This one says use synthetic division to divide this by x plus 8. Use the result to find all the zeros. So again, I wanted you to really get a firm grasp of when to switch the sign before delivering it to the synthetic box and when not to switch it. When the value is part of an expression like this and you're going to break these two apart, that is when you switch the sign. Okay, then we're going to take the coefficients here. 1 for my cubed term, 17 for my squared term, 90 for my first degree term, and 144 for my constant. Put the line underneath it and begin multiplying. Drop down that first value to get the ball rolling, and it's going to be -8 times 1, -8. Add these up, you get 9. -8 times 9, -72. Add these up, you get 18. -8 times 18, and you get -144. Okay, so because this zeroed out by using this number, that means that this actual value is a 0, or in other words, a solution for this third degree equation, the third degree function. So I already know one of my 3 answers. I know there are 3 solutions, or what we call zeros, 3 zeros. And I've already found one of them, because any number that, when synthetically divided into polynomial, creates 0 in the remainder column, is actually a 0 of the function. I also, by doing this, have brought this down to second degree. That's what these string of numbers means right now. You just have to reattach the variable. So this is your second degree term. If you started with third degree term, this is a second degree expression, with the first term being the coefficient of the second degree term, second number being the coefficient of the first degree term, and this being the constant. And we want to know what would be the zeros or the solutions of this remaining second degree solution. So a lot of these, we've just factored them. Okay, you can use guess and check here. In other words, break up the x squared. That's what goes in the front 2 positions. And then think of 2 numbers that you can multiply to get 18, but also add to get 9. And that would be 6 and 3. Okay, 6 times 3 is 18, the C value, but they also add up together to give you the B value. Okay, so then looking at the factors that remain and asking ourselves, what x value would zero this out? And that would be x equal to -6. So that's a solution. And then what value would zero this out? X equal to -3. And I have completed all 3 solutions. Okay, last problem. This would be number 11. Solve the equation 2x cubed minus 61x squared plus 4x plus 5, given that 1/3 is a root. So just another one with a fraction. Now notice that this one, again, making a distinction between when to switch the sign before you deliver it to this box and when to leave it alone. Okay, this value was part of an expression. To break that bond, you need to switch the sign. This is not part of an expression containing x, so do not switch the sign. Okay, you're just going to use it as is. Put that 1/3 there. Oops. Pencil's about to break. Let's get another pencil. Okay, so I'm going to do 1/3 right in here. I'm going to stretch these out. We do have a 3rd degree term, a 2nd degree term, and a 1st degree term, and a constant. So 12 is the first coefficient, -61 is the second coefficient for 2nd degree, 4 is coefficient for 1st degree, and 5 is the constant. Put that line underneath, drop down the first number. And again, you may have to come out to the side to do the arithmetic if you can't do it in your head, which is fine. Okay, so we're going to be multiplying 1/3 times 12 and then delivering that product right up here. So what is 1/3 times 12? Well, that would be 12 divided by 3, 4. Okay, and then you're going to go -61 plus 4, combine those two numbers, and get -57. Okay, next we're doing 1/3 times -57. I believe that's -19. Yep, -19. When we multiply this times this, -19, toss it right up here, add these two together, you get -15. Now we're doing 1/3 times -15. So 1/3 times -15 is just 1 times -15, -15 at the top, divided by 3, -5. So put that right here, add these up, and you get zeros. So we have once again started the problem with a value that zeroes it out. And notice that this time they used a different word. So let's go over all the things that mean you have a solution. You can say that it's a root. You can say that it's a zero. You can say that it's a solution. All of these mean that every single one of these words, and on a graph it would be called an x-intercept, meaning that if you took that number and plugged it into the equation, everywhere there was an x, you would get a 0. All of these things mean that. Okay, so what we have now at this point is one of the answers. Given that 1/3 is it, this is one of the answers. And we want to find the other two. There's 3 altogether. This is the equation that we now have, or the polynomial that we now have. We have 12x squared, because remember, we've come down to 2nd degree by making this one synthetic division pass through the polynomial. We have a -57 as the coefficient of our 1st degree term, and a -15 for the constant. And we want to know what are the remaining zeros resulting from this 2nd degree equation. So we can try and make these numbers. I think 3 goes into each of these. Well, let's try that. We know 3 goes into that, and that's pretty easy. -57 divided by 3, that's -19. So we can make these somewhat smaller by dividing everything on this side by 3 as well as this number by 3. So 12 divided by 3, 4, makes that coefficient smaller. -57 divided by 3, I just popped that in my calculator and it was -19. And -15 divided by 3 is -5. So this makes it a little bit more doable. And we're going to factor. I would suggest splitting the middle term as the factoring method here. I mean, you can use guess and check if you're good enough with your factoring. A lot of students like splitting this middle term, and this is how that goes. You're going to start by looking for 2 numbers that multiply together to give you whatever the A times C value is. A times C would be -20. So you're looking for 2 numbers that multiply to give you -20, and there are plenty of them, but these 2 numbers also have to add together So this was created by multiplying a front coefficient times back coefficient. That's the A and the C value. And the two numbers we come up with that multiply to give you negative 20, they better also add to give you this number, the B value. Okay, easy enough. If you go 20 times 1 and you make one of them negative, you're going to get a 19. But you want to get a negative 19. So if that be the case, you can make the larger number negative, so it will be the ruling sign. When you add up this negative and positive, you'll get negative 19. And when you multiply them, you'll get the negative 20 that you want. So easy enough to find. I'm demonstrating a technique called splitting the middle term. It is a factoring technique. So we are going to use these numbers that we just came up with, negative 20 and 1, to rewrite the middle term so that we continue with our factoring. Okay, this is for factoring, this technique. So leave the front term as is, and instead of negative 19x, we're going to write negative 20x plus 1x. And those two combined is the negative 19 that you just had a second ago. And then bring down that negative 5. We have now taken this 3-termed polynomial and stretched it out into 4 terms. And so now what you can do is finish the factoring by using the method factor by grouping. Because you can group the front 2 terms. This is for 4 terms, factor by grouping. You can group the first 2, noting that 4x is part of this, and 4x is a factor of this. So you can take out the greatest common factor belonging to just these front 2 terms of 4x, put a single parenthesis next to it, and ask yourself 4x times what gives you 4x squared? X. 4x times what gives you negative 20x? Negative 5. Then go look at the back 2 terms. The only thing that these 2 terms have in common is the number 1. So that would be the greatest common factor for those. You always put a single parenthesis next to the common factor that you pull out, and you ask yourself that times what would give you that back again? X. This times what would give you negative 5? Negative 5. Excuse me. And continue. When you're doing factor by grouping, you're taking out a common factor 3 times. I did it once here for the first 2 terms, took another common factor out for the back 2 terms, and now I'm going to take a third common factor out. Treat this as 1 term, and this is the second term. What these 2 terms have in common is x minus 5. And what goes in the other parentheses are these first and second common factors that you took out, 4x plus 1. And there you have it, all factored using a technique called splitting the middle term. So what are the remaining zeros or solutions or roots, whatever you want to call it? Well, what makes this 0? X equal to 5. And what makes this 0? Well, maybe you can do that in your head. It is negative 1/4. Maybe you can't. Maybe you need to just say, okay, what makes this 0 by setting it equal to 0 and solving it as though it was a little mini equation. You would be bringing this over here, making it negative 1. You would then have 4x is equal to negative 1, and you would divide that 4 off, resulting in what I just said, that the 0 for this particular factor is negative 1/4. And there you have the one that we found by synthetic division. They told you it was a root, and that's the same thing as saying that it's a solution. And we proved it to ourselves, and at the same time brought this 3rd degree polynomial down to 2nd degree, 12x squared minus 57x minus 15. Try to write a little bit clearer here. I'm not running into that negative. Okay, we then reattached the variables. This was my squared term. This was my 1st degree term. This was my constant. I made all of those coefficients smaller by noting that every single one of these coefficients was divisible by 3. That brought me down to 4x squared, negative 19x in the middle, and negative 5. And then what I demonstrated was a way to factor this called splitting the middle term. Okay, and that allowed me to find the last two answers, positive 5 and negative 1/4. Negative 1/4. 5 made this factor a 0 and therefore was a solution, and negative 1/4 makes this value a 0 and therefore is a solution. So these are your final three answers. Okay, that concludes section 4.3, and we did numbers 6 all the way through 11, examples 6 through 11.